Welcome to the last of the Café Size this summer. Welcome to Bigelow. Are there any people who have never been here before? A couple of hands. Welcome. Well, we're most excited to see you, although we're happy to see everybody. Welcome to Bigelow. So we are an independent research institution. We're not affiliated with any university. We have been around since 1974. We were started by two real visionaries in the field, Charlie and Clarice Yench, and have been doing just cutting edge science for almost 50 years. We were originally on the west side of town. We had kind of a rabbit warren, apparently, of space, some outbuildings. There was a molecular lab and a former garage. We leased the space from the state, and the joke was we paid $1 a year, and the joke was we overpaid. So they moved into this fabulous building in 2012. It is not only beautiful, it's probably the most well-designed facility to do research that I've ever seen. We could not operate and do what we do without our dedicated board members. And since I haven't said this for the last couple of times, I know we have some there. Could all the board members or former board members please stand up? And advisory board members?
Come
on, ladies. It is so important for an organization our size to have people that, as our current chair, Bill Burgess, says, are willing to give their time, talent, and treasure. And we are so grateful to have it. We've got a number of supporters here. Thank you so much for the support you give us. As a nonprofit, there's a lot of things, especially exploratory research, that is difficult to pay for. And so donations really allow us to spur on some of the big innovations we've been able to do. We have about 100, we're up to 105 actually, full-time staff that are here all year. We go up to about 150 in the summer. So I think our students are almost leaving us soon. It will be very sad, and we will also breathe a sigh of relief, because it is, while they're here, we really put them through their paces, and it's a lot of fun, but it's also an incredible amount of work, but they leave with a great, great experience. As I said, we thank our donors. H.M. Payson is a Maine-based financial advisor who has been supporting this Café Size series for many years, and we're very grateful to them. They've not only been supporting this, but they've been great advisors for us over the years. For those of you that are online, if you have any questions, there's a question and answer button at the bottom of your screen. So put the questions in, and Fritz will be monitoring that. For those of you who have questions, we'll stop midway through the talk and then at the very end of the talk. And so try to remember those questions, and we'll try to get as many of them answered as we can. So now it is my distinct pleasure to introduce Ben Twining. So Ben has been at Bigelow since 2008. He came to us from a tenure track position down at the University of South Carolina. He became the first vice president at Bigelow in 2016 and really was responsible for taking this laboratory through a very, very dark time with the loss of the previous executive director. He served as the interim director for a number of, how long was it? You probably know exactly down to the day and hour, Ben. And so has just been an incredibly important leader for this laboratory. And he also shepherds an enormous number of education programs. And one of these, Café Size, we need to do an overview of the education programs we do, because they're so inspiring. And sometimes all of that makes us forget what a fantastic scientist he is. So Ben studies iron. It is one of the elements in seawater that limits the growth of phytoplankton in vast regions of the ocean. And so it's one of those variables that is also very important to understanding how the ocean will respond to climate change. So he is an international leader. He's going to be leading a international expedition to the South Pacific and then down into the Southern Ocean this fall as part of a GeoTraces program, and is just an all-around fantastic human being. And we are so, so lucky to have him. So with that, Ben Twining, take it away.
Thank you, Debbie. Very kind. Great. Well, good evening, everybody. I'm I'm actually really excited for this talk. It's a talk that I haven't given before on a topic that I'm just delving into, and this is a great opportunity to explore these ideas with others. And it's a little bit of a serious subject, but I've been told that I should warm you up with some humor. So I've got a joke. How many scientists does it take to screw in a light bulb? Anyone? None. They use them in double-blind trials, I guess. I don't know. I just Googled it. All right. It gets better from here. Don't worry. Okay. So I'm going to talk today about the topic of carbon dioxide removal, the idea of using the oceans to remove carbon dioxide from our atmosphere. And this is, I think, a bit of a daunting subject, but one that I think its time has come that we need to be talking about it. And hopefully I will convince you of that during this talk. Okay, so climate change is the motivation here for sure. And I think it's clear, certainly to me, that climate change impacts are growing and are becoming increasingly visible. And I could have put hundreds of newspaper sort of clips up here to demonstrate that. I picked 3 all from the last week or so. Extreme heat in Europe, heat records in the UK. Of course, any single record doesn't demonstrate climate change, but they're consistent with the trends of climate change. Growing risks of fire in the West and in Australia last year. And closer to home, there we go. Can you see? There we go. This. Closer to home, challenges for our local shellfish industry. This is a op-ed by Bill Mook talking about the challenges that climate change present to local shellfish farmers. So climate change is here and it's only going to intensify. But sometimes even with those headlines, it can be hard to sort of visualize and feel climate change. So I think this is an interesting comparison. This is a website that will predict what the climate of a city will feel like in 60 years based on an average of, oh.
They'd like to turn it on. It's at the bottom of their screen.
Great. So Debbie's reminding me we have closed captioning available, and you can turn it on at the bottom of your screen. We've turned it off here so that I don't get distracted. Thank you, Debbie. Yeah. Right. So Portland, Maine is predicted to feel like Baltimore in 2080. And I think I haven't spent much time in Baltimore in the summer, but I don't think it feels like Maine in the summer. And I think that's a pretty good motivation to worry about this topic. Okay. Well, one of the drivers, probably the primary driver of climate change, is increasing atmospheric carbon dioxide. And probably most of you, hopefully all of you, know that. This is sort of the iconic measure of carbon dioxide at the Mauna Loa Observatory on Hawaii. And it was started right before 1960 by David Keeling. And it shows, a pretty steady increase, in fact, an accelerating increase in carbon dioxide concentrations, starting below 320 parts per million back in the late 50s up to almost 420 parts per million now. And to put that in a little more perspective, this is that same data plotted against the atmospheric carbon dioxide concentrations for the last 800,000 years. And we know this because we can collect ice cores from Antarctica and collect the carbon dioxide that's trapped in the bubbles of that ice. And you can see that it has fluctuated, but it's never basically gone above about 300 parts per million over that pre-human time period. But it is only during the industrial age that we're now seeing this exorbitant rise. And it's not only going up much higher than it's been in the past, at least in this record, but also it's going up much faster. And that's also a great risk for climate change. And to provide a little more context, during the last interglacial period, so about 100,000 years ago, sea level was about 20 to 30 feet higher than it is today. So this gives us a sense of the type of climate that existed before humans were the dominant force we are, and a sense of what we might expect given enough time for the Earth's climate to respond to the carbon dioxide that we've emitted. And this is something that I think we should all be very aware of and trying to deal with. Okay, so one of the problems, an additional problem, I should say, is not only that carbon dioxide concentrations are increasing, but that our emissions, actually the rate at which we add carbon dioxide to the atmosphere, are also still increasing. So this is a figure showing annual fossil fuel carbon dioxide emissions. It's in units of gigatons of carbon dioxide per year. I've been told that the average person doesn't know what a gigaton is. So I've converted this to 1 gigaton is 10,000 US aircraft carriers. I'm not sure that makes it that much easier to understand, but it's a massive amount of material. It's a massive amount of carbon dioxide. But every year we emit, well, in 1970, we emitted about 15 gigatons of carbon dioxide. And now we're emitting about 35 gigatons of carbon dioxide. And this increase has happened at the same time that major efforts have begun internationally to reduce these emissions, right? So in the 1990s, the Kyoto Protocol was adopted. In 2015, the Paris Agreement that got a lot of fanfare was adopted. And after each of these, of course, carbon dioxide emissions, not just concentrations, but emissions have continued to increase. In fact, you can see here that actually it is the economic downturns that have driven carbon dioxide temporarily lower. Oil crisis in the 70s, collapse of the Soviet Union in the 90s or late 80s, global financial crisis of 2008. These are times where we saw pauses in the increase of emissions, but generally they are continuing to go up. And this also shows how closely connected carbon dioxide and the economic health of our world are, and how closely connected carbon dioxide and human health are and well-being. And this shows how difficult it is to address this without harming our quality of life. Come on through, science. That was intense. Yeah, that was like planned. Okay, well done. Yes. So, given these not only increasing concentrations of carbon dioxide and increasing rates of emissions, it's important to recognize that it is not enough only to eliminate our emissions. We actually need to remove carbon dioxide from the atmosphere. And the reason for that is because carbon dioxide is a greenhouse gas, and it serves as a blanket warming our planet. And so this is a cartoon showing energy coming into the planet in the yellow arrows. This is energy radiation from the sun. About a third of that is reflected off the Earth without entering. And about 2/3 is absorbed by the Earth. That then heats the Earth and it emits that energy back out as infrared radiation as heat. And if I can find there we are. And that heat, this is coming out here in this red arrow, is then absorbed by this blanket of carbon dioxide and other greenhouse gases. And it's emitted back down to the ground. That is the greenhouse effect. And so as we add more carbon dioxide, it's like we're adding more layers to that blanket. And what's happened is that we are now out of energy balance. We now have more energy coming in than is going out, and that's why our world is warming. But we're sort of behind the times. It takes a while for the Earth system to catch up to that extra energy. So just like if you get into bed and you're cold at night and you pull up an extra blanket, a warm comforter, you don't warm up instantly, right? It takes some time for your body to warm up. And then once you get to the middle of the night and you wake up and you're too hot, a little sticky, and you have to actually take that cover off, right, to cool down again. And that's the same situation here. We need to not only stop adding carbon dioxide, but we need to remove some of these layers of carbon dioxide in order to bring our temperature back to a manageable level. So this is a graph that tries to show this. I showed it with a cartoon. Let's try it with a graph. This is showing why carbon dioxide must actually be removed to stabilize this. So on the left here, this is a graph showing the temperature anomaly in degrees Celsius. So this is temperature normalized to the beginning of the 19th century. We'll call that 0. And then this is the warming of the Earth, averaged over the entire Earth over the last century or so. So you can see it going up. And then this is what's predicted to happen for temperature in the future based on different carbon dioxide emission scenarios. So red is if we continue to increase our carbon dioxide 2% per year. Orange is if we keep it constant. And over the last 5 or so years, we've been a little bit above constant. And the green and blue lines are what if we actually decreased our carbon dioxide at, say, 3% per year or 6% per year, really starting immediately. And you can see that those will, if I can find my cursor, those will slowly start dropping the temperature of the Earth back towards what we might call the maximum we've seen over human time. Holocene is the time that humans have lived on the Earth largely, or where we've evolved. And you can see that you will get back to that safe maximum, but it takes almost 200 years to do that. And that's a really long time. And if you think about taking your drink with its ice cubes and putting it under your bed with your blankets, I'm not sure why you do that, but if you did, you can imagine that those ice cubes don't melt immediately, but over time they will. And so the longer that drink stays under your sheets, in this very strange analogy, the more it will warm up. And so what we want to do is actually reduce that temperature and increase the speed at which we get back to a safe temperature. And the way we need to do that is by actually removing carbon. So on this graph on the right, this is the same predictions from models, but with adding carbon dioxide being removed from the atmosphere. And you can see for the same emissions assumptions, so either 2% per year increasing or down to 6% per year dropping, if you then also take out additional carbon, you can bring our temperature back to what we think is a safe temperature by the end of this century. And what these are showing, I should mention, each of these there's a number, and it's, say in this case, 153 PGC, and that stands for petagram of carbon, another unit, but a petagram is equal to a gigaton. So what this is saying is that even if we decrease our emissions by 6% per year, we still will need to take out potentially 150 gigatons of carbon dioxide to get back to a safe level just by the end of this century. And what we need to get to essentially is about 350 parts per million. And some of you may have heard of the nonprofit advocacy organization 350.org, and that's where their name comes from. That is thought to be close to sort of the safe carbon dioxide concentration. So I also want to point out that this need has been recognized actually for a number of years now, and it's actually built into the assumptions of international climate planners. So this is a statement from the Intergovernmental Panel on Climate Change. This is the international body that sort of tries to figure out climate for us. And the statement says all pathways to limit global warming to 1.5 degrees C warming project the use of carbon dioxide removal on the order of 100 to 1,000 gigatons of carbon dioxide in this century. This carbon dioxide removal, or CDR, would be used to compensate for residual emissions in order to return our temperature following a peak in temperature. So this is already being assumed by scientists that are modeling our climate, but yet the research we need to inform this is really missing. So here's another way to think about the need for this negative carbon dioxide emissions. Here again on this graph, we have again carbon dioxide emissions on the y-axis, gigatons per year. And here's what we might think of as sort of the business as usual scenario. We're going to continue to increase our emissions, and then at some point in the future, they'll decline. But if we are going to stay to a scenario where we keep our temperature below, in this case, say 2 degrees Celsius, then what we need to do is not only remove all these carbon dioxide emissions in green, and we can do this through sort of what we might think of as conventional abatement technologies, so solar, wind, hydroelectric, moving to non-fossil fuel energy sources. But that will still leave some carbon dioxide emissions that are really difficult to get rid of. These are in the brown. So these might be things like airplanes. It's really hard to figure out how to put a heavy battery in an airplane. So it is likely that we will continue to use fossil fuels for air travel for a while. So in order to counteract those, we need this blue area. We need these negative emissions that, when subtracted from the brown emissions, will result in a net emission that becomes negative in the future. And that's what this red is showing. So these are these negative emissions that we need that require carbon removal technologies. So that's what we're going to be talking about. How do we get this carbon out of the atmosphere? And this is needed on an order of about 10 gigatons per year. I know it's a number that's hard to put into context, but try to keep that in your mind, about 10 gigatons. Okay. So I wanted to step back one step and talk about the term climate intervention or geoengineering. So what we're talking about here has been termed geoengineering in the past. This idea that we might sort of turn a crank and engineer our climate. And I think that term represents a level of precision and planning, which is probably inaccurate. And so the term climate intervention has become a little more of a favored term among scientists, because I think it better communicates both the need for that intervention, but also the lack of sort of an engineering specificity about it. And when you think about climate intervention, there's sort of two ways that you might group the things that could be done. One is to actually try to have less of that energy come into the earth at all. And that is called solar radiation management. And I'm going to show you one slide after this to sort of talk about that, just to give you a sense of that. But that is not what we're doing research on at Bigelow, not what I'm advocating for research on. But I do think, actually, I will say it is important to study that, because it may also be needed at some point, but it is not what we're talking about here. On the other side is to actually, again, remove carbon dioxide and lower the thickness of that blanket. And sometimes this is also called negative emissions technology. So those are sort of synonyms. Okay, but I do want to talk about solar radiation for one slide, because I think it's important to know that it is sort of an alternative to carbon dioxide removal. So these are some of the sort of ideas that have put forward for decades now on what might be done if you needed to cool the earth and you couldn't remove carbon dioxide or remove carbon dioxide in other ways. And generally, these are around the strategy of increasing the reflectiveness of the earth. So having some of that solar radiation bounce off, either by building buildings that are reflective, by planting potentially crops that are reflective, or most likely by trying to increase the cloud cover on the earth, because clouds reflect some of that energy away. And there's actually pretty good evidence that this would work. And some of that comes from the eruption of Mount Pinatubo in 1991 in the Philippines. And this volcanic eruption, ejected massive amounts of ash and sulfur dioxide aerosols into the atmosphere. And what those did over time is they created little nuclei that clouds formed around. And so they created increased cloud cover over the earth and spread over the earth. And in the 2 years that followed this eruption, the average temperature of the earth declined by about 0.5 degree for 2 years. So it was notable. It actually could be studied. It also, it's worth noting, changed precipitation patterns in the earth, and it changed crop yields. Actually, so some crops became less productive. So there's real negative consequences as well. There's negative consequences to everything. That's the message tonight. But it is a strategy that has merit as being feasible, I should say. It's also worth, come on through scientists, everyone's welcome here, that actually this approach is already being tried or studied in some small scales. So this is an article about an experiment that the Australian government is funding to study what's called marine cloud brightening, the idea of spraying sea salt aerosols from a ship. Maybe you can see it. This boat has what looks like a snowmaker, and it's spreading these salt aerosols above the water, and that causes clouds to form. And they were doing this to try to protect the Great Barrier Reef, which is experiencing these severe bleaching episodes. And so this is, again, just research, experimental, to see if this would help. But already this research is going on, and it's important to know that it's a thing we should be paying attention to. But for the rest of the talk, I want to focus on the other strategy, which is carbon dioxide removal. And there's a number of ways to do this. And so I'm going to sort of talk you through some of the parts of this cartoon. And we're going to start on the land. So one of the strategies that international climate planners has sort of said might be possible, might be a solution or a strategy, is what is called BECCS here. That's not a very sexy acronym. It stands for Bioenergy with Carbon Capture and Storage. That's probably not any sexier. But the idea is that you would actually burn biomass, trees, other plants that are growing on land, burn them for energy, collect that energy, and then capture the carbon dioxide and put it underground. So the plants are taking up the carbon dioxide as they grow. You're turning it into energy, and you're capturing that carbon dioxide below ground. So it sounds pretty great in theory, I would say, but it hasn't been demonstrated at any scale yet. And it has another problem, which is to scale it up requires massive amounts of land to grow the biomass needed to support this at any scale you'd need. So it needs a lot of land and a lot of water and fertilizer to support all that biomass. Another approach that seems perhaps a little less in sort of intrusive would be afforestation. So planting trees in areas that don't have trees to take up carbon. Also, would work, but requires massive amounts of land and water to implement on a useful scale. Another idea is what they call enhanced weathering. So adding chemicals to minerals on the earth that would speed up their ability to take up carbon dioxide. Again, it's an idea that's just getting some research now, but would be very difficult. It would require massive amounts of land. And the third one is called direct air capture. And this is the idea that you have fans that actually pump air through a filter that removes carbon dioxide, and then that is pumped underground. And interestingly, that's one of the first that has started to be scaled up. This is a screen grab of a facility that has already been built in Iceland by a company called Climeworks. And it is the first large-scale direct air capture plant. And what it does is actually pumps air through these filter fan regions, extracts the carbon dioxide with some chemistry, and puts that carbon dioxide into geothermal reservoirs in Iceland, where it reacts with minerals and turns into a solid substance. So it sounds great, but it requires a huge amount of energy. So of course you have to create energy to make this work, and it also requires, like other land-based CDR, it requires massive land and water. And if you think about the scale needed, this website is promoting that this has a capacity of up to 4,000 tons of carbon dioxide per year. So remember, we said we need to get to gigatons. If you wanted to remove a gigaton of carbon dioxide, you need 250,000 of these plants. So this just demonstrates the scale. The point here is not to badmouth this particular technology, but to point out the limitations of all of these technologies, because they all have limitations. So this leaves the ocean as one of the potential areas where we might study this. And there's 2 points I want to make before we have our first break. The first is that the oceans are already a major sink for carbon dioxide. So this graph is showing where carbon dioxide that we've emitted since really the 1860s in this graph is going. So on the positive y-axis, that's gigatons of carbon dioxide emitted. And on the negative part of that axis, it's where they're going. So here you can see these rising emissions in gray from fossil fuel burning. And below, we can see that some of that has gone into the atmosphere, maybe 40 or 50%. Some of that has gone into the land, into biomass on land. And about a quarter to a third of the carbon dioxide that humans emitted has gone into the ocean. So it's already serving as a sink for carbon dioxide. And I think we should be grateful that it is serving that function even without us doing anything. But it demonstrates that this capability is already happening naturally to some extent. Another important point is that the oceans already store 50 times more carbon dioxide than the atmosphere, and about 15 times more carbon than the land. So the oceans, the deep and the intermediate and the surface ocean, if we add these numbers together, these are in units of gigatons. Our unit of the night, it's about 38,000 gigatons of carbon. And if we compare that to the amount of carbon dioxide in the atmosphere, it's less than 1,000. So again, much higher amount of carbon dioxide, and even compared to the land, where there's only about 2,000 gigatons. So even a small percentage in increase in the amount of carbon dioxide taken up by the ocean could lead to a notable change in the atmospheric carbon dioxide concentrations. So some sort of conclusions for the sort of first half of this talk, where I've tried to introduce this topic and the need for this topic. One, I hope I've been clear that we must reduce carbon dioxide emissions as soon as possible. There is no other solution that doesn't involve mitigation of emissions. But we must also research ways to remove the existing atmospheric carbon dioxide. It's not enough just to stop emissions. Additionally, there's no silver bullet. So if you're looking for one at the end of this talk, I'm going to disappoint you now. There is no silver bullet, but the oceans may provide an opportunity for carbon dioxide removal. So I'm going to stop there and hopefully take some questions to get us started. And then I'm going to talk about the research that Bigelow and myself are doing on this topic. So thank you. Who's got a question? I must have said something that aroused you.
Ben, my question is, can you hear me?
Mm-hmm.
My question is, what does that do to the ocean balance for biomass with considerably more carbon dioxide? Alternatively, what does it do when you bury the carbon dioxide in the earth?
In the earth was your second part? Yeah. So what does it do to put all this carbon dioxide into the ocean or into the earth? Well, I think it varies. I think that there are, with the example of that Climeworks plant, there are places where you could put the carbon dioxide in the earth where hopefully it would react and form a mineral. You'd sort of reverse a process that's happened in the past. And it might be relatively stable there. It might be relatively innocuous. There's other places where folks have thought about putting carbon dioxide into former oil, sort of fossil fuel repositories where they might be under pressure. I think has more possible side effects or failure points, for example, if it has to be sort of held under pressure. I think ecologically, we don't know much about what's going on in those environments. Beth Orcutt, who is in the back here, who studies sediment or deep sea geological environments, I think would probably agree that we don't know much about these environments under the earth. And so it'd be ignorant of me to say that it's a less harmful place for it, but hopefully it would be a less a more inert environment. I think in the ocean, it has a couple effects. Obviously, well, maybe not obviously, ocean acidification is one of the effects. As we add carbon dioxide to the ocean, it increases the acidity, and that certainly has negative effects on biology. But some of the carbon actually is in a form of bicarbonate and carbonate that doesn't cause harm. So the main point is that you can probably get some additional acidification, but it depends on what form that carbon is in. And I'll talk a little more about that in the second half. But great question. Is there another one? Yeah.
All right. So what types of organisms would be processing the carbon? And then you mentioned it briefly about acidification. So if we have increased CO2 in the water, that's going to change the chemistry of the water. How does that then affect those life forms that are processing the CO2?
Right. So putting more carbon dioxide in the ocean will definitely change the chemistry, as we talked about. Yep. And generally, if some of that carbon, and I'll show some slides about this coming up, if some of that carbon actually makes it to the bottom, it might not increase the acidity of the ocean. It might not turn back into carbon dioxide. But for the carbon that does, it will increase the acidity. And so therefore, it will have impacts on organisms. And I think we need to increase, we need to better understand that. And we're going to need to weigh that against the other impacts that it's going to have. I'm definitely not telling you that there's a lunch here. But that's an area that of probably about a decade of solid research. And we need to continue that research, particularly probably on deep sea organisms, if this was to come to pass. Great question. Yeah, another one.
Okay. I've got a question. I lived out here 15 odd years ago, and this place was here, but you couldn't come up here. It was private. I mean, it was whatever. I wondered what took place then that is different now that we can now come in here.
You're talking about the laboratory itself? Yeah, so this building was built in about 2011. So prior to that, it was just undeveloped land. There wasn't anything here, as I know it, prior to that. I remember I was at the groundbreaking. So yeah, there wasn't anything on this land. It was undeveloped.
I couldn't hear her.
There wasn't anything.
Oh, sorry if that wasn't.
So it was a different place.
Well, it was just woods, right?
Yeah, it was woods, undeveloped land. Yep.
Okay.
Maybe we could talk at.
We hear numbers of gigatons and massive, and isn't it science fiction? Is it likely that we can ever manage? I mean, if you just look at the volume effect at the Earth here, how much more volume there is of atmosphere, and that CO2 is all smushed around all over that atmosphere. To me, it just feels like science fiction. We'll never be able to manage anything that massive and do anything to it.
Yeah, so I don't know if you've ever heard that question. The question is that it feels so massive. It feels like science fiction that we might ever be able to manage that carbon dioxide in the atmosphere. And I'm not telling you that we can. One of my main message tonight is that I think that we need to be studying this to see if we could, if we ever needed to. But my response, I guess, is that I think 100 years ago, it didn't seem possible that humans could have the impact on the atmosphere that we have had, right? It might have seemed that we were just a small, component of the Earth system, and we've now become a major driving component of the Earth system, right? We have changed. You saw the carbon dioxide graph. We've increased that concentration. That's by human activity. So we have been this driving force in the global carbon dioxide cycle already. Can we reverse that and go the other direction? I don't know. It will require massive effort. Should we? We'll need to think about the costs of that. But we are going to be facing some other very significant costs as well. And I've tried not to dwell on that, but 20 to 30 feet of sea level rise, which wouldn't be by this century, but grandkids and great grandchildren will also have great impacts. And I think we're going to be forced to at least think about these options that we're faced, which I think will be a number of bad options. But I do think it's reasonable. I think Debbie, as a nitrogen expert, am I correct that humans now emit we've sort of doubled the nitrogen cycle of the world, right? We make so much fertilizer and we convert atmospheric nitrogen to fertilizer, and we create about as much as the natural processes do as well. So we have demonstrated our ability to move these global cycles for better or worse. I don't think it's crazy to think it. Yeah. Maybe one more? Yep. And then
Sorry.
we'll have another time for questions. So
There's also the issue of methane. I
Yes.
understand that methane is as bad, if not worse, than CO2. So how do you mitigate the methane?
So that's a great question. How do we mitigate methane? And when I gave this practice talk yesterday, I was told to take methane out. I was told to keep it simple. Don't talk about methane. And I feel very I'm grateful that someone has brought it up. But you're right. The short answer is but you're right. CO2 is not the only greenhouse gas. There's methane, there's nitrous oxide, there's chlorofluorocarbons. There are other things, and they also are important. And a little bit there, what's shown here in the sort of other greenhouse gases. And you can see that this sort of cartoon scenario reduces the carbon dioxide more than it reduces the methane and other greenhouse gases, because they will require probably different functions, different strategies to abate. One of those we've been working on at Bigelow, which is to try to feed seaweed to cows. So I think some people have talked about it. Debbie mentioned that a couple of weeks ago. I'm involved in that project. There are other efforts to try to figure out how, first of all, what the sources of the methane are and how to deal with that. But it's a great point. There are other greenhouse gases. I've just sort of simplified it as carbon dioxide. But yeah, very good point. Should I keep going, Debbie? Okay. Great. I hope she will. Okay. So I want to spend the second part now talking more specifically about research happening at Bigelow Laboratory on ocean carbon dioxide removal. And this is a sort of a reminder cartoon. This is put together for an issue of the Bigelow magazine Transect, which has an article, this most recent issue, about some of these CDR research efforts. And just to remind us, there's a sort of a couple of ways that people have talked about increasing the uptake of carbon dioxide or carbon by the ocean. One is something sort of as pleasant sounding as ecological restoration. So increasing the coverage of mangroves, salt marshes, seagrasses that grow in local areas that are known to take up carbon dioxide in sort of coastal sediments. So that's one area where folks are working here. So Doug Rasher, for example, is working on understanding local kelp communities. Another strategy 2 here is seaweed farming. So it's been proposed internationally and also being studied even in Portland, whether we might farm seaweed and use it not to feed cows, but actually to sink it to the bottom of the ocean as a way to move carbon. And so Nicole Price is studying that here and a team she's leading. Another strategy up top is to do ocean alkalinization. So this is sort of adding tums to the ocean, if you will, adding bases to try to counteract the carbon dioxide addition that's acidifying the ocean. And so if you added minerals to the ocean, it might raise the pH, lower the acidity, and also increase the amount of carbon dioxide that could be stored in the ocean. And Steve Archer's working on that. And then there's fertilization, both adding materials from ships and also trying to artificially move deep water up to the surface, because deep water tends to have higher concentrations of nutrients. And Steve Archer and his group have been working on that with colleagues in Europe. These are some pictures of these large mesocosms, these large bags of seawater. Here they're placed, I think, floating off the Canary Islands, where they can test and sort of try out these strategies of upwelling and alkalinization to see what it does to the community, to start to understand its effects. So Steve's been involved in that. I think I already mentioned Nicole and her work that she's leading with others here, Pete Countway, Manoj Kalamathan, so on seaweed farming. So I want to recognize them and encourage you to read the article if you want to hear more about their work, because I'm going to talk about my work for the rest of this. And this is work focused on ocean fertilization. So the idea between ocean fertilization is that you add nutrients to the ocean to speed up what we call the biological pump. And this is another cartoon, like our cartoons here, that sort of demonstrates how this might work. So in the ocean, what tends to happen is that carbon dioxide dissolves on the surface of the ocean naturally, and it increasingly goes in as CO2 goes up in the atmosphere. And that carbon dioxide is converted into plant material, phytoplankton, by photosynthesis, by phytoplankton. And much of that if not most of that, is actually converted right back into carbon dioxide by bacteria and zooplankton and other little critters that eat those plants. And so that carbon dioxide can cycle right back out of the ocean. And so actually in the ocean every year, there's 90 gigatons, we're good at those gigatons now, 90 gigatons of carbon dioxide go in and out of the ocean through this process. But some small fraction of that organic carbon, that phytoplankton, sinks below the surface. And when it does that, it brings the carbon associated with that plankton material from the surface ocean, where it's in equilibrium with the atmosphere, down to the deep ocean, where it's sort of capped and not in equilibrium with the atmosphere. And that essentially pumps carbon from the surface to the deep. And we call it a pump because it's going against the gradient. There's higher concentrations of carbon in the deep ocean because of this process and a couple others than there are at the surface ocean. So this is pumping carbon down. And this biological carbon pump takes up about 10 gigatons of carbon per year. It's about the same level, just to keep this all in context, as we actually probably need to remove from the atmosphere each year. But it happens naturally. And the idea here is that this process might be enhanced by adding nutrients. So those nutrients may essentially increase the community. It may, if you add the right nutrients, increase the sinking rate of those, and that might increase this flux. So the idea is that you're basically priming the biological pump. So in order to think about doing this, we need to think about, well, what would you add? If you wanted to increase the strength of the biological pump in the ocean, what would you add? So we need to think about what nutrients are limiting the growth or the productivity of the ocean, the strength of this pump. So this figure is sort of an estimate from a model of what's limiting growth of plants in the ocean in various places. And each color corresponds to a different resource for phytoplankton. So in the red, that is a lot of the Atlantic and Western Pacific and some of the Indian Ocean. That's nitrogen. So nitrogen is one of the most important nutrients that limits the growth of plants in the ocean. So in some places, you would need to add nitrogen to cause more growth. In other areas that are shown in green here, like particularly in the sort of subtropical Western Atlantic, phosphorus is what limits the growth of phytoplankton. So you need to add phosphorus. In some parts, it's yellow. Yellow indicates light. So certainly in the really high latitudes under the Arctic and the Antarctic, they get less light. And so light is often what's limiting growth rates in the ocean. And then you have the big blue mass, which takes up a lot of the Pacific Ocean and the Southern Ocean, this area around Antarctica. And these are waters that we know to be limited by iron. So in these areas, you'd add iron to stimulate the biological pump. And the difference between these three nutrients, nitrogen, phosphorus, and iron, is our thinking about how much you'd have to add to stimulate carbon uptake. So if we think about the composition of phytoplankton and the relative amounts of these materials that they contain, for every atom of nitrogen you add, you might get 7 atoms of carbon produced by phytoplankton. For every atom of phosphorus, you might get 100 atoms of carbon produced. But for every atom of iron, because it's needed in such small quantities, you could potentially grow 100,000 atoms of carbon in phytoplankton. So because iron is a trace nutrient, the idea is that you could add small amounts of it, relatively small amounts of it, and create a large increase in the phytoplankton biomass. So this idea the importance of iron has been demonstrated by the presence of unused nitrate and other nutrients in the surface ocean. So this left figure shows some data showing the concentration of nitrate, nitrogen nutrient, in the surface around the global ocean. And these areas that are yellow or green, again, in the Pacific and largely in the Southern Ocean, are areas where there's excess nitrogen. It's waiting to be used in some senses, you might think. And it has been allowed to accumulate because there's not enough iron. And the reason that there's not enough iron, largely, is because these areas don't get much dust. So on the right, I have a satellite picture. You can probably sort of see it in the back. This is a dust plume that's coming off of the northwest coast of Africa. So this is the Saharan desert, and we can see natural processes carrying this dust out into the Atlantic. And this dust has a fair amount of iron in it. It lands in the ocean, some of that dissolves, and essentially fertilizes the Atlantic with iron. And it's one of the reasons why the Atlantic is not thought of as an iron-limited area. So iron, we know, is a key nutrient in these ocean processes. So the connection, first of all, the recognition of iron as a limiting nutrient, but further, the connection between iron and climate was actually first sort of discovered and promoted by a scientist named John Martin, actually went to Colby, class of '69. And he made a very provocative quip at I think a sort of a cookout at Woods Hole back in 1988, where he said, "Give me half a tank of iron, and I will give you the next ice age." And this is maybe the most famous quote in oceanography. I think I'm sort of obligated to repeat it to you in this talk. And it's obviously a scary idea, and it is certainly not what we're promoting, but it definitely succeeded in stimulating several decades of research into this idea, this connection between iron and climate via the biological pump. And now, sort of in this case, 30 years later, this data really has come together to demonstrate that there is a link between these functions in the ocean. So in this data, we're going back in time in an Antarctic ice core again. Here, we're going back to about 160,000 years on the right. And the gray data show dust. This is dust getting into the Southern Ocean. No humans involved, right? This is happening naturally. And you can see that there were dustier times and less dusty times. And what we see is that during these dustier times, there was also more biology. And that is known by this chemical called an alkanone. It's like a chemical signal of phytoplankton productivity in the past that we can measure in these ice cores or in these sediments. And you can see that in the past, when it's been dustier, there's been more biological productivity, more carbon sinking to the bottom of the ocean. And additionally, we can see that these have been times when there's been lower carbon dioxide in the atmosphere. So there's this inverse correlation between iron getting into the ocean productivity, and global carbon dioxide. And so this is it's been termed the iron hypothesis. It was promoted by John Martin, and it's largely been proven that there is a connection. It's not the only connection, but it is a real connection between adding iron and global carbon cycle. So the other thing that his famous quip did is it stimulated 15 or 20 years of open ocean experiments where scientists went out and added iron to the ocean in what we call mesoscale experiments. These are experiments that might be tens to hundreds of square kilometers in size, and look to see what happened. Does the community respond? Does carbon get taken up? And so this map is showing the locations of those experiments. There are these white crosses largely. And you can see they're in these areas of high nitrate. This again is nitrate, surface nitrate in the background. So in these yellow and red areas, scientists went out and added iron and looked to see what happened. And I was lucky enough to be a graduate student and participate in one of these. So I participated in the last US-funded experiment in 2001. There were 2 patches that were fertilized south of New Zealand. I went and found this picture in the olden days. This is the scientist from the back of on the ship. That's me, bright-eyed, bushy-tailed, third-year graduate student, Ben Twining. But this was, a great opportunity to sort of see this experiment in action and see the response of the community and the response of the carbon cycle to iron addition. So these experiments occurred for about 15 years or so. And during these 15 years, it stimulated growing interest and also concern about this idea of ocean iron fertilization, or OIF. And so that came from a couple of things that were happening simultaneous to these scientists' experiments. There were companies that started forming to try to do this, to commercialize this. So Climos is one of them. Planktos was another one. These are companies that were started not with nefarious missions at all, but with the idea that you might commercialize this, that you might do this process and sell carbon credits, for example. But the scientific community, I think, in consensus was that there wasn't enough known to get to this process. There was a lot of concern that the sort of commercial side was moving ahead of the research, where the research was. There was also this concern led to revisions of a couple of treaties, the UN Convention on Biodiversity and the London Convention and the London Protocol, which now basically preclude ocean fertilization experiments from happening due to these concerns. So there's now sort of legal protections in place that we would need to change if we wanted to do this research on a large scale. This happened during this decade. And the final of these experiments, which was called a low effect, scientists are very good at these very catchy acronyms. This was led by German and Indian scientists. And it really resulted in a real sort of groundswell amongst the international environmental community with concern about the growing number of these experiments. And so actually, while they were en route to their site to do the experiment in the Southern Ocean from South Africa, they stopped. And I think they actually sat there for 2 weeks and did an additional environmental impact assessment before they were allowed to proceed. But this really it came to a head, I think, with an experiment that happened off the west coast of British Columbia in 2012, where an American company to promote ocean fertilization, convinced one of the native populations, the First Nations of Canada, to do an experiment where they added iron to try to stimulate the salmon productivity. And it really was sort of raised the ire, I'd say, of the science community, because they felt that it wasn't done transparently and it wasn't done in a way that we could really tell if it worked, and that sort of the effect was being oversold for what we understood it to be. And so sort of the accumulation of these concerns really led to the cessation of this research in about the sort of early 2010s. And many in the scientific community, myself included, sort of stepped back and said, it feels like this is going faster than the science is ready for. And it seems like, there's a lot of concerns here we have. And so it sort of took a pause. But during that decade, as I've shown, carbon dioxide did not take a pause, right? We've continued to emit, we've continued to grow our emissions as a human race. And in 2019, a new report came out from the IPCC on the oceans and cryosphere and this changing climate. And this just brought home in really clear terms and growing terms the effects that climate change is having on the ocean. Warming, sea level rise, ice melting, permafrost melting, heat waves. It's a depressing list. And it really brought home, certainly to me personally, thinking about it, that doing nothing is also not solving this problem, right? Humans are not, as I've already mentioned, reducing our carbon dioxide emissions. And so this has stimulated myself and a number of scientists, I think, to re-engage in this process and to say, listen, we need to bring science to this. It's also brought companies back into the process. And I think scientists are increasingly saying we need to work together. We cannot disengage if we have concerns in this. We need to be part of these conversations to make sure that this research is done to inform these decisions that we have in front of us. So I want to end by talking about two areas of research that I've been involved in to try to do this, to try to so what's an example of how we might do research on ocean iron fertilization to understand its costs. And one of them is to understand how we might deliver iron more efficiently. So I want to talk about how inefficient this process has been in the past. So if you want to do an ocean iron fertilization experiment, this is the pictures of the one that I participated in. You've got to bring these large shipping containers of some form of iron. In this case, this is iron sulfate, FeSO4. It comes in powdered form, and you have these big bulk containers of it. You bring it out to sea, and then you dump it into big tanks. So these are 5,000-gallon tanks. You fill them with seawater, you add this iron, and then you have to add acid to dissolve it, because iron is not very soluble in seawater. And then you drag a tube or a hose behind your boat, and you release this acidified iron-rich water into the environment. And when you do that in the Southern Ocean, you can create a bloom, as I've already talked about. So this is a satellite image. It looks like a smile, doesn't it? It's not a smile, but it's a satellite image of a chlorophyll bloom, a phytoplankton bloom. This was created in the Southern Ocean by a different experiment, the Soiree experiment. And it's striking. It works, right? You add the limiting nutrient and you get a carbon response. But additionally, we found during these experiments that you actually lose most of your iron right away. So these are measurements of iron in the water. And over the 2 weeks of this particular experiment on the right. So here you can see these days since the start of the experiment. And the black bars are basically the addition, the infusion of iron into the ocean. This is how much iron we added. And the blue circles, the blue dots, are our measurements of iron, what we were actually able to measure in the surface of the ocean after we added it. And you can see that, 1 day later, we see some areas where there's elevated iron, but already, even just a day later, a lot of the water that we've measured has lost that iron. And after 2 or 3 days, it's 75% of it has been lost. And then the scientists in this experiment added it again, and they added it again, and they added it 4 times in total. And each time you see a relatively rapid loss of that dissolved iron. And so the scientists then tried to make a budget of this. We like to make budgets. We're practical people. And so here, this budget shows these are these 4 iron additions of infusions over the 2 weeks. And they calculated that they added about 1,000 picomolar. Doesn't really matter what that is. It's a unit of concentration. But of those 1,000 picomoles of iron that they added, only about 5% of it actually turned into biology, only turned into the phytoplankton that we're hoping will take up carbon. About 90% of it was lost into the particulate form. It just precipitated and sank out. So these experiments have been shown to be really inefficient. And rather than sequestering hundreds of thousands of atoms of carbon per atom of iron, they've sequestered thousands. It's been much less efficient. And so one of the questions is, can we improve that efficiency? If we wanted to do it, is there a way we could improve it? And so at Bigelow, this is one of the things we've been working on. And I've been collaborating with Dave Emerson, another senior scientist here. And Dave is a microbiologist who studies bacteria that oxidize iron. They live on iron. And so this is an electron micrograph of one of these cells. This is a teeny little bacterial cell. And to make a living, it doesn't eat organic matter, it eats iron. And it oxidizes that iron and turns it into a different form. And it takes dissolved iron and it turns it into these beautiful stalks. And these are actually its waste product. And when you do this in great amounts, you can actually get, it's probably hard for you to see, but you get these beautiful orange pools that happen. These are actually taken in the Booth Bay Peninsula, areas where you get these naturally occurring bacteria oxidizing iron and creating these iron oxides. And Dave and I got talking about these iron oxides and the fact that they're very, very small, so they might not sink as readily as the other iron that was added to the ocean. And they're also combined with organic molecules in a way that we think might make them available to phytoplankton. And so we did an experiment. We actually recruited an undergraduate from Colby, Sarah Beth George, who's now a PhD student at Brown, to do experiments where she would add some of Dave's oxides, these biogenic oxides, to phytoplankton to see if they would grow and respond. And this is one of Sarah Beth's results. That's her senior thesis. This graph shows the concentration of phytoplankton on the y-axis and time on the x. And the top line here is basically the growth of phytoplankton if we add the iron in dissolved form, like we normally would. And you can see they grow quite well. And the orange line is if you don't add any iron. And you can see they don't grow at all, showing what we know, iron is needed for growth. And these middle two lines are experiments where we only added these biogenic iron molecules. In this case, it's a genus called Leptothrix, which is sort of cool. There's a picture of it in the water. And so you can see here, these kinds of experiments demonstrate that you can grow phytoplankton, you can accumulate carbon through the addition of other forms of iron that might be more stable. They might be actually readily producible in a more friendly way. And they may make ocean fertilization, if we wanted to do it, more efficient. So this is one sort of flavor of the research that that's been going on. And David actually put in a patent for that technology. The second area of research, which is quite different, that I want to talk about that I've been involved in, is actually using modeling, so not lab experiments, but using modeling to try to understand the effects that ocean fertilization might have on fisheries. And so this is a prediction. This is a map showing the predicted change in maximum fishery catch potential in 2050 compared to 2000 in the face of climate change. So no fertilization here. But the areas that are red are areas where there are predicted to be decreasing fish catches. And you can see there's a lot of the ocean that's red. And this is one of the predictions of climate change, is that the fisheries may become less productive in certain areas. There's also dark blue areas where it's predicted to become increasingly productive, I should say. But one of the reasons for this is because as the ocean warms, as the surface ocean warms, it creates a more distinct layer of less dense water at the surface that doesn't mix with the water below it that has a lot of nutrients. And so it keeps those nutrients from coming to the surface. So what we wanted to know was, would ocean fertilization make this better or worse? And the mechanism here is what scientists call nutrient robbing. And this is the idea that that water in the Southern Ocean, so here's Antarctica, you can see that, might be hard. Antarctica, this is the water in the Southern Ocean around Antarctica. And it has a lot of nutrients that aren't used because of iron limitation. I've shown you this, right? Lots of nutrients in the Southern Ocean. And those nutrients, when they're not used, sink down and they move northward below the surface and they come back up at the equator. And they support productivity at the equator because they weren't used in the Southern Ocean. So if we add iron to the Southern Ocean to draw down carbon dioxide, we're going to draw down those nutrients as well. And that might rob the nutrients that would make it to other latitudes to support fisheries. And we wanted to study this to see what impact it might have. And so I worked with a couple of computational scientists. One of them, the lead author or the lead scientist, is a Brit named Alessandro Tagliabue, shown here. And so we used a model that he runs to simulate this occurrence. And on the left, on the left, this is the prediction of what would happen to fishery biomass. So all the fish. So we've taken a climate model and we've linked it to a fisheries model. And here we have, again, gigatons of carbon on the y-axis and time going from 1950 to 2100. And the black line is what we expect to happen with climate change in this model. So you can see this shows decreasing fishery yields with climate change. And the blue is if we also then do iron fertilization on top of it. So here we've started fertilizing right in the 2000s, and you get a boost of productivity initially, but then you get a drop over time. And actually, over time, this model predicts less fishery productivity due to iron fertilization. And if we look at where that's predicted to change, that's the figure on the right. So these are red is increasing fishery biomass and blue is decreasing. And you can see in the areas where we add iron, like the Southern Ocean, you get a big increase. So more fish in the Southern Ocean. But the blue areas are areas where it's predicted to have less fish. And that includes a lot of the lower latitude areas where a lot of us fish. Not us, me personally, but a lot of societies fish and have their economies that include fishing. And so this really demonstrates, well, I should say actually, so before I say that, these models, I should say, have significant uncertainties. So this is one model, but it demonstrates the type of effects that are happening and the need for us to sort of constrain those uncertainties in these models. So we took this one step further, one more graph here, and looked at the specific nations that were going to be predicted to be impacted by this fertilization. And here, this plots all of the exclusive economic zones. There's 250 EEZs, there are coastlines that are shown here. And I've plotted them by their continent, and their symbol size is their GDP. And on the x-axis, it's the predicted percent change in fishery biomass. So if you're to the left of the line, you're going to be a loser. You're going to have less fish, predicted to have less fish for fertilization. And on the right, those might be some of the winners. And there's a lot of ways to look at this data. And in the interest of time, all I'm going to say is that most of the countries are losers in this sense. Now, they might win in other ways, right? They might win because there's less sea level rise, or there's less ocean acidification because of lowered carbon dioxide. But the fisheries will likely be affected. And very few of the winners are wealthier nations, right? Or sorry, the few winners are generally wealthier nations. And many of the what you might call losers or more affected countries tend to be places in Africa, lower latitude countries. But this really demonstrates the potential unequal effects of any climate mitigation or scheme that we really need research to understand. So I just want to finish with sort of this point that this raises obviously many, many big questions, important questions about this research. And just, a primary one might be who gets to make any climate intervention decisions. There are certainly many others that could be asked. And my goal certainly is not to answer this, but to point out hopefully that we need to do this research so that we have information to inform these decisions when they face us. So to take home messages, first of all, we must reduce our carbon dioxide emissions. Climate dioxide removal is no antidote for emission reductions, and that needs to happen immediately. But it's not enough. We also have to remove carbon dioxide to stabilize our climate. It could have significant costs. There's definitely no free lunch here, but the cost of not reducing carbon dioxide may be higher, and that's what we need to research. And finally, we definitely need research into the efficacy and the costs and the risks of this type of activity to inform decision making. So finally, we've been asked to sort of leave the audience, leave you with sort of what can you do, right? It's hard to get this information. I find it hard to work on this topic. So, my answers are not necessarily simple, but I would certainly urge you to try to reduce your carbon footprint, each of us to reduce our carbon footprint. Individual actions are not going to solve this problem, but I really feel that in the wealthy country of the United States, we have a moral obligation to do what we can to reduce our footprint. Additionally, I encourage you to support policies that are reduce carbon dioxide emissions. Whatever your political flavor, ask your representative what their plan is for tackling carbon dioxide, because it is a nonpartisan problem that we face. And finally, support research into this because I really think it's important. And thank you. Happy to take more questions.
This is all incredibly noble work, and I think what a lot of your research has shown is
Is that on?
No, it's not. Okay. It shows how inefficient so much of this is and how much scaling up we would have to do, even if we didn't have the political component of people being against it. But what do you think the role of scientists are in population reduction and less cows? So instead of we're as scientists struggling to figure out all these ways to fix some of these things by tinkering with this, tinkering with that. And yet there are two big things that we could do, but I don't know if you believe scientists should meddle in that part of it.
Interesting. Well, so it's interesting to use meddling at the end of that question, obviously. I think I've increasingly in the last few years come to the position that I think scientists, that at least me personally, and I think other scientists need to have a strong voice in this. You're right, it is tinkering. The major changes are changing our energy systems. But I also feel that science alone, obviously science alone cannot solve this. I mean, issues of equity and justice, which we're increasingly becoming aware of, are so important to this. There's not a technological fix, right? Because any fix is going to be expensive. It's going to impact people differently. So scientists have a role to inform. I think we need to be allowed a voice to be really honest about the stark decisions that we're going to face in the future. I mean, I've tried to do that here in a way that doesn't make you all totally depressed. Hopefully we can all go back and, have a good dinner. But they are stark, and I feel like I face them increasingly every day, and scientists need to be open about that. These are bad decisions, but ones that I think we're going to have to face. And so I think scientists need to be open about that. Is that going to move the needle? I'm not that optimistic about it. It has in the past, right? Many bold scientists have been saying these things for years, and it hasn't changed. These are really hard things to change. But I think we can do is try. I don't have any great answer there, other than I think we need to be doing more to bring people's attention to it, including, in some sense, even talking about this. People say, I can't believe you would even think of working on this. The moral hazard of, giving the sort of get out of jail free card to emitters. I hear that. And I say, it's not really that simple, right? I think we have to be open about the costs and start dealing with it. I don't know, maybe these kinds of talks will bring that to light in a different way. We'll see.
So absolutely incredible presentation. I'm sure we all really appreciate it. Dr. Bronx gave a presentation a couple of weeks ago, and she put up a slide that showed carbon dioxide concentrations, zooplankton, bacteria, phytoplankton, and that was extremely thought-provoking. And I would have liked to have asked a lot of questions at that when you just answered way more questions than I could have thought to ask. It seems that, the Earth is definitely good at buffering itself. And I would think that maybe atmosphere is the first buffer, and plants fixing carbon into soil. And then maybe upper ocean is the next buffer, absorbing from the atmosphere. And then you have the deep ocean, and obviously that's extremely critical and a huge place where carbon gets fixed. So I kind of wonder about your thoughts about, how the buffering is moving into the more critical areas. And one last thing, you mentioned iron sulfate, and you said that it just kind of disappears. I'm sure it's getting dissolved, it's getting diluted. Have you considered maybe how iron sulfate moves into deeper ocean, and if there are any effects there that could be contributing to fixing carbon?
Sure. So I think I'm going to summarize that as two things. One is, what do we think about buffering capacity? There definitely are a lot of systems buffering carbon dioxide, and the ocean has been an important one for sure. And there is an additional level of concern that goes further into the chemistry of carbon dioxide in the ocean that suggests that as we add more carbon dioxide, the ability of the ocean to take up carbon dioxide decreases. So I think we have certainly scientific reason to expect the ability of the ocean to buffer to decrease, both due to chemistry and also because warmer waters absorb less gases as well. So as the ocean warms, it will take up less carbon dioxide. And there was a great New York Times headline a couple of years about this, which is something to the lines of, the ocean may stop being our garbage collector in a few years, which I thought was an interesting way to put it. You also asked about iron sulfate. So the iron is added as iron sulfate. It dissolves in acid, and then it basically precipitates right away. So when that acidic solution mixes with the relatively basic ocean, it actually turns into iron oxides. It's just sort of like those stalks, but they're not as pretty and small as those stalks. It makes bigger particles and they tend to sink, and it removes it to the bottom of the ocean where it's probably totally inert, honestly. And interesting side note, that's sort of exactly what happened in the environment in the world 4 billion years ago, or 2 billion years ago when oxygen was first introduced. There was all this iron in the ocean, and suddenly organisms started creating oxygen, thank God, and it caused all the iron to precipitate in the ocean sort of at once, and now created this low iron ocean that we have. So I think we know pretty much what's happening. I don't think it's going to do much in the deep ocean, but it's not very useful to us there for sure. Yeah, we need to keep it in the dissolved phase so that it stays up in a form that plants can use. Yeah. Thank you.
I believe that the oceans are being overfished. So I'm curious how you can determine the effects of the environment versus the overfishing that man is doing.
That's another great question. Yeah, she said she feels like the ocean's being overfished. And how do you compare these impacts with fishing impacts? So again, when I gave this sort of a practice version of this yesterday for Bigelow colleagues, one of the first comments I got was, you need to say that overfishing is the biggest impact on fish in the ocean. And I didn't do that, did I? I didn't get a good job getting that message in there. But you're totally right. Human, impacts on fish are definitely removing more fish than decreased productivity is. And that's another complexity of this system. Often we think of this system, this era is now the Anthropocene. That's sort of part of geological time when humans are a major actor on Earth and Earth systems. And fish is another example of that. We are controlling fish abundances as much as these nutrients are. So they're not accounted for in that model. It's a very simple model. And your point is really well taken. We need to be considering how this impacts fishing, how fishing regulations impact this. You're right. Lots of social science needed to better understand this. Thank you.
We got one from online. I think we're out of time after that.
Oh, yeah. Sorry.
One from online about iron, though. Do you believe that producing and transporting biogenic iron and iron bacteria and/or could be cost effectively scaled up? Have you made any back of the envelope calculations on this and predictions?
Yeah, so the question was, could this be cost effective to add biogenic iron to the ocean? So Dave Emerson has done, actually a group of us at Bigelow have done a fair amount of work on that in the last year. And it depends on a lot of assumptions, but I think that it could be cost effective. You probably wouldn't do it you wouldn't drag it around behind a ship. You might put it up into the atmosphere so that it blows over these oceans. And so atmospheric processes actually might help it dissolve as it rains down. I know that sounds scary. It still sounds scary to me, but I do think I think that there's a good argument can be made that it could be cost competitive with these other strategies, or with dealing with hundreds of feet or tens of feet of sea level rise, right? I mean, let's not forget the cost that we are going to incur if we do nothing as well. So yeah, happy to talk more about that with the online person, whatever they want. Yeah, thank you. Yeah.
So with that, can we thank Ben for a fantastic talk?